or the second moment of area is an indicator to resistance of bending. Okay, bending or buckling. Okay, it is an indicator. Okay, so what do I mean by that? Okay, the higher the higher the second, or the higher the I value. Okay, so put down here comma I, the more resistance to either buckling or either bending or buckling. Okay. So for this case, right, we know that by comparing, by comparing IY and IZ, and knowing that IY is going to be less than IZ. Okay. So from here, we can say that buckling, therefore, buckling will occur, okay, about the YY axis or on the XZ plane. Okay, buckling will occur on the XZ plane. Okay, so now we will bring this figure back into play. Okay, I'm going to put this figure. For this case, I'm going to calculate both. Okay, I'm lecturing now, and I want you to visualize this. More important than anything else. Okay, so I'm going to take this. And I'm going to paste here. Okay. So we are going to calculate a few values, and I want you to see, right? So we are going to calculate PCR about the exact plane, and this is equal to pi squared E multiplied by IYY over by LE squared, right? So this is equal to pi squared. And the Young's modulus given to us is 200 times 10 to the power 9. And our IYY value is 819.24. Okay, so 819. Wait, and let me move things around. Times 10 to the power minus 9. And it happens that our equivalent length are the same. So the equivalent length is 6 squared. Okay, so this will be giving us pi squared times by 200 power 9 times by 819.24 power minus 9 divided by, so pi squared times by 200 power 9 times by 819.24 power minus 9 divided by 6 divided by 6. is equal to 44.92 times 10 to the power 3 Newton. Okay, so that is our critical load. Okay, and then from here we can immediately also calculate our factor of safety. So the factor of safety is equal to PCR over by P applied. So this is equal to 44.92 times 10 to the power 3 divided by the P applied. So the applied load that was given to us is 16 times 10 to the power 3. So this is equal to 44.92 power 3 divided by 16 power 3 is equal to 2.808 safety of factor. Okay. Now, if we were to do on the other plane, which I want you to compare. So over here we have PCR, okay, and now this is on our XY plane. This will be equal to pi squared E multiplied by IZZ over LE squared. Okay, so this will be equal to pi squared 200 times 10 to the power 9 multiplied by 7.752 times 10 to the power minus 6. And the equivalent load are the same. So this is equal to pi squared times by 200 power 9 times 7.752 power minus 6 divided by 6 divided by 6 is equal to 425.0. Okay, so what we have is 425.051 times 10 to the power 3 Newton. Okay, and if we want to calculate our factor of safety over here, this is equal to PCR divided by P applied. Right? So this will be equal to 425.051 times 10 to the power 3 divided by 16 times 10 to the power 3. So this will be equal to 425.051 divided by 16. The safety factor is 26.566. Okay. So you can see from here, right? What you can like visualize from here is the buckling will occur on the what? On the XZ plane or about the y-axis when the load is 44.92. Okay. If we were to apply 425 Newton, okay, or 425 kilonewton, buckling will occur in the exact plane already. Okay, so as I said, this example, I think it's a really a good example for you all to visualize what second moment of area could do for us. Okay, so in terms of summary in this example, okay, I'd like to do summary for this example. What have we learned? Okay, so if we were to look at this example, we are able to determine how to calculate I about different axes, right? And the And the general rule parallel to axis of interest is the width, and then perpendicular to axis of interest is the what? Is the depth. Okay. And what we realized also, when the equivalent length are the same for both planes, okay, buckling will occur when the second moment of area is lower. Okay, that's what we have learned. If the equivalent length are the same, when the equivalent length are the same, okay, when equivalent length is the same, okay, it means that the end condition, okay, end conditions for both planes are the same. Okay, so this is what we have learned and what we have. I'm showing you the example on how to identify or how to calculate your second moment of area, and also when to use IYY and when to use IZZ. Okay. Right. Oh, another one. The when to use IYY or IZZ is dependent on the buckling deformation curvature. Okay. So like what I've shown you guys before is this, like the highlighted in yellow. That's what it means. Okay. Right. Now we are going to do another example. This example builds up on what we have in example number 1. But now the end conditions are not the same. I repeat again, the end condition now are not the same. Okay. And let's look at this example. So we're going to proceed with example number 2. And it's a very interesting example. Okay, and I'll tell you why. Right. So this is the example that we're going to do next. Okay. And example number 2, I'd like to highlight there's optimization going on. Okay, there's an optimization going on. And again, it is not more difficult or whatsoever. It's just it lumps in a lot of parameters that you have to consider. Again, as I said, it's not more difficult. Okay. You won't see anything new. The only thing you see new is the equivalent length. Okay. Right. So from here,